We've spent a couple of videos now exploring the microcanonical ensemble, the ensemble within the Gibbs approach that allows us to calculate the entropies that we can use in thermodynamics. Here, I want to use the same approach to calculate the entropy for the Einstein solid that we've already seen. But before I do that, I want to sort of break down the different kinds of problems that we encounter in the microcanonical ensemble. We've already seen some of these, and so hopefully this makes some sense. Oops. So along this axis, I want to talk about distinguishability. So we have distinguishable particles versus indistinguishable particles. And then, because I'm thinking of states that have non-interacting particles, really this whole diagram is for non-interacting particles, I just want to think about whether or not the energy levels for any one particle have maybe like two values or more than two values. So two energy states or greater than two energy states. Now here, in the two energy states and distinguishable particles, that was where we found, that was where we found the ideal paramagnet. For indistinguishable particles with tons of different energy eigenstates, in fact, an infinite number of energy eigenstates that scale like n squared, we found that that we got the ideal gas. Now, I don't mean to imply that only one such system lives in each of these. We could have, of course, said that the particles were all distinguishable in the last system, and we would have gotten a slightly different entropy because we would have ignored that 1 over n factorial factor. That would have pushed that gas system into the distinguishable particles, but with more than two energy states. All I mean to suggest by this chart is that we need slightly different methods for each of these cases. Technically, this 1 over n factorial factor that we used for the ideal gas is not the exact way to do that problem. We'll see in a future lecture a more careful treatment. But for indistinguishable particles, there will typically be something like a divide by some factor kind of approach. For distinguishable particles, we had a very easy time when there were only two energy eigenstates because the combinatorics were pretty easy. So in that case, we were able to say we definitely needed to go in the positive direction some number of times and in the negative direction some number of times. And then we were able to use the choose function to finally get the entropy. We'll see that when we have more than two energy states, we have a slightly harder time of things. But this is where we find the Einstein solid, which is what I want to talk about today. Okay, so the Einstein solid, rather than coming from the particle in a box, comes instead from the quantum harmonic oscillator. So just to remind you, for the quantum harmonic oscillator, we have some sort of parabolic potential. Excuse me. So this is parabolic. And it's a parabola given by 1/2 times m, where m is the mass of the particle, times some parameter omega squared times x squared. Good. And we find in quantum mechanics that the energy eigenstates here are given by En, which is h bar omega n plus 1/2. Good. Now, for the sake of this video, I'm actually going to neglect the 1/2 here. The reason I'm going to do so is that it doesn't dynamically affect anything about the physics. The reason is basically I choose choosing not to neglect the 1/2 here would just mean that when I fix an energy U, I need to shift that energy up by the number of particles times 1/2. So it's fine to neglect here. Okay, so I'm going to neglect this. So now, when I have when I have a large number of harmonic oscillators, well, then the state is just given by n1, n2, up through n capital N, where there are capital N harmonic oscillators. And this is just going to be h bar omega times the sum, k goes from 1 to capital N, of n sub k. Good. Maybe not too surprising. Okay, so now if I fix a u, and once again, I'm going to say that that's a, an integer, times, in this case, h bar omega, and I want this to equal h bar omega nk, sum over k. This is, if I want to, so finding the number of solutions to above equation is the same as finding the number of solutions to, I guess I'll write it down here as well, a is equal to the sum, k equals 1 to n, of n sub k. All right. In other words, how many different ways are there to break A into capital N different parts? And this is where this distinguishability versus indistinguishability question becomes very important. Are those parts distinguishable from each other or not? In other words, suppose that we had two parts and I wanted to break A into them. Suppose A is 11 and the parts are of size 5 and 6. Do we count 5, 6 as distinct from 6, 5 or not? If the parts are distinguishable, then we do. And if they're not, then we don't. In the field of combinatorics, this corresponds to this a distinction between integer compositions and integer partitions. Integer partitions would count 5, 6, and 6, 5 as being the same. They don't care about order. Integer compositions do care about order, and that's what we want here. So, answer is number of integer compositions of A into n parts. Okay, great. Okay, so to find the number of integer partitions is a challenging problem within combinatorics. And for different kinds of cases, like different restrictions on those partitions, this can be quite involved. Fortunately, because we're in the distinguishable case, that's not what we have here. And integer compositions are a little bit easier to work with because of the following method that we can take. Let's use an example again of A is 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, great. Now, we want to take these 11 objects and break them into, let's say, 4 groups. Well, to break them into 4 groups, we're going to need 3 dividers. So we could put a divider here, another divider here, and a third divider here. Why not? And as we think about it, there are 10 spaces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we need to choose 3 of those spaces to have dividers. The rest won't have dividers. So if we mandate that there's at least one object between each set of 2 dividers, then we would get, if at least one object between each set of dividers, then number of compositions is exactly 10, which is 11 minus 1, choose 3, which is 4 minus 1. So I can write 11 minus 1, choose 4 minus 1. Great. Now, we have to modify things very slightly when we are allowed to have dividers right next to each other, which is the case for us here. But I'm actually not even going to go into it because these numbers will be large, and this actually already gets the correct scaling behavior. All right, great. So what we need is something like, we need approximately the number of that we're trying to divide, A. Breaking it into n parts is like choosing n. Great. Okay, so here we are. This is the basic, or this is an approximation for the answer. If we want to find the number of solutions to u is equal to this expression, the answer is that that number is approximately A choose n. Good. So where does that leave us? Well, the entropy for the Einstein solid can now be written down pretty easily. It's just Kb log of that number. Okay, so now let's write that using Stirling's approximation. Remember that we wrote down a corollary that allowed us to expand out the choose function as well. So if I maybe just say what S over Kb is, it's going to be A log A minus N log N minus A minus N log A minus N. Excellent. And remember that A is U over H bar. So this is U over H bar omega. H bar omega log U over H bar omega minus N log N minus U over H bar omega minus N log U over H bar omega minus N. Now at this point, you're probably sitting at your computer screaming. And that's because when we derived this before, these n's were 3 n's. So what's going on here? Well, n is the number of one-dimensional harmonic oscillators that we have. What Einstein assumed when he derived this model was that at each point in the lattice, there was an independent harmonic oscillator for each direction. And so rather than having one n of these, there are 3n because we're in 3 spatial dimensions. And in d dimensions, you would have d times n. So we can comfortably replace each of these n's by a 3n. Notice also that this has allowed us to figure out what u naught way back in lecture 6 was. U naught was h bar omega. It was just given by the angular frequency of those individual oscillators. Wonderful. So now we've seen in a few cases that the Gibbs approach gives us exactly the behavior that we expect. In the next lecture, we're going to see that the microcanonical ensemble is not all that there is, and that in fact we can make our lives a little bit easier than having to do hard combinatorics problems by using the notion of temperature. I'm excited to do that, and I'll see you then.